Hello everyone, my name is Joshua and I'm an early stage researcher and an audio engineer for over a decade now. And today I'll be talking about auralization and active sound design with spatial audio on a vehicle simulator. So in this talk, I'll give a short introduction and a little background about myself, what I do and what is my research, and also the importance of automotive audio. And I will touch a bit upon active sound design and also give a brief introduction about spatial audio. Also, thanks to Harsha, he has covered a nice overview of binaural audio and convolution, which also I'll be covering a bit on. And I'll be talking about my research that I'm doing and the current work and the future works. So I work as a research engineer associate at Siemens, which is located in Belgium, in the nice city of Leuven, and our office looks like this. It's a beautiful campus out there. I work in the acoustics team in a project called Gap Noise, which is funded by the European Union. I'm also doing a PhD in mechanical engineering with focus on acoustics, uh, which is also located in the city of Leuven. The university name is KU Leuven. Before this, I did my master's in sound and music computing from Maynooth University in Ireland. And I did my bachelor's here in India on computer applications. And I also hold a diploma in audio engineering from Music Launch School of Audio Technology. So my research focus is on spatial audio, acoustic, NVH technologies, and sound synthesis. So this picture, this is my life for over 10 years. And I'm sure you all also can relate to this. We go to the studio or our mixing space, we make music, we mix for hours. Bass is tight, it's punchy, highs are nice and crisp, and everything is on place. And we go and play it back in the car, and we know what happens. It doesn't sound good, or sometimes it sounds great, but we can never judge how it's going to sound in the car before. So, why is it? Because cars or any vehicles are complex spaces with speakers located in weird positions. So it's important as musicians and audio engineers to understand the space our audio is going to play back. So it's important to consider that cars are not just a mode of transportation anymore, but a space to listen to music, to feel emotions, and to spend time while traveling. So now, before I get into the topic, I will play two sounds and I want you to all to tell me which one sounds more powerful and sporty. Okay, raise of hands. Who chooses A? Not surprising, no one. And who chooses B? Great. Now I'll play two more sounds and you have to tell me which one is faster. Okay, who chooses A? No one, no surprise. And who chooses B? Everyone. So, my friends, you did not see any accelerometer. You did not feel the wind on your face, or you did not see how fast the car is going. But how do you know that this car is powerful? Or how do you know this car is going this speed? So, it's important to understand the auditory senses. Even without visual cues, we humans have the tendency to identify certain emotions, not just emotion, but also the perception using our auditory sensors and audio cues. Which brings me to the topic of active sound design. So manufacturers, they don't just keep it as theory, but actually implement these theories into actions when they build a car or manufacture a car. So music producers who are a combination of engineers and music producers. They sit and design the car's sound, how it should sound on the exterior and how it should sound on the interior. So active sound design is a process of artificially generating and modifying vehicle sounds in real time to enhance driving experience, emotion, and safety, especially in electric and autonomous cars. Even though it's a creative process, there are certain rules and regulations that we have to apply. There are like some certain engineering rules and also rules and standards from the government on how loud it should be on the exterior, how it should be on the interior for safety and perception. And the most common methods that producers or the engineers use in this technology are order-based synthesis and granular synthesis, which is a familiar model of synthesis, which you guys are an expert more than me. So this is an interesting graph of a comparison between ICE vehicle, an internal combustion engine, versus an electric vehicle. As you can see, the ICE as the powertrain noise or the engine noise predominantly taking over the overall contribution of the sound. But when you go to the EV, the sound has completely reduced. The powertrain noise came from 50 to 15%. And the main contributors of sound now is road and wind noise. So how do we approach it? So through active sound design and through active noise cancellation, we implement this technology into these cars to create brand sounds, specific brands of specific car sounds, and also to make the passenger comfortable and also make the space more pleasurable. But it doesn't just stop there. More than EV, the future of cars is autonomous and smart mobility, where there is going to be no drivers in the cars, and it's going to drive around automatically. And there are going to be complex speaker systems placed inside the car with a lot of sensors outside the car as well, like ADAS, like radar, LiDAR, and a lot of cameras. So as engineers and musicians and composers, it is important for us to have tools to design sounds for these platforms. So we cannot build an entire car and then test. If it doesn't work out, we go and scrap the car. No, it doesn't work like that. We need a simulation system where we can actually implement these technologies, test, analyze, and we make decisions even before building the car. That's where my research comes in. So my PhD research topic is sound synthesis of autonomous vehicle, where the goal of this PhD is to develop a framework for rendering real-time, event-dependent spatial audio cues, moving and static. Once that framework is developed, we evaluate vehicles' operational conditions and also the passengers' physiological and psychological reactions, and to finally understand the correlation between vehicles' acoustic attributes and our psychoacoustic factors. Because even though we make the most finest sound of the car, at the end of the day, humans are going to sit inside the car. So it is important to evaluate the psychoacoustic characters of humans as well. So how we do that? We do a lot of measurements. So this is me wearing a binaural head and sitting inside a car. And we also use stereo and other methods. So what we do is we do several maneuvers like a run up, goes down, which is like we raise from 0 to 100 or come from 100 to 0. And also we measure constant speed and we synthesize these audios. So we use these measurements, and along with this, as Arsha showed in his previous slide, we also use an anechoic chamber. We take the same model of car inside, and we also measure the cabin's impulse response and the cabin's response and apply to this algorithm or tool. So what this tool does is take a limited set of measured data and give us unlimited data. So basically, based on the throttle position, we can predict how a sound is going to play in that specific position. And the sound can be decomposed into orders and broadbands. Orders are just harmonic contents, like how we use in chords, like let's say a C chord, and broadband is just the background noise. And we record this total sound. And we break it down into orders. So this is just the engine noise that you hear now. And we then separate the background noise. We heard a lot about source separation today. It's similar to that, but we separate orders here. So, but now the challenge is the passengers are not sitting in the car upright, and the driver is not holding the steering and focusing on the road anymore. So there are no drivers in the autonomous car, and the technology is evolving. So it offers new challenges for engineers and creatives in this platform. First is you're not paying attention to the road or your surroundings, and you're in random positions inside the car playing games or something. So how do we approach it? So you cannot have a fixed head position. You cannot have a driver and three passengers. So now everyone is considered a passenger, and we need to make sure everyone inside the car is aware of the surroundings and aware of the alerts that is coming from different directions. So we use spatial audio technologies for this. So what is spatial audio? Spatial audio is generally a three-dimensional audio experience where sound is coming from all the directions. It can be rendered from multiple speakers and also can be acquired using specialized microphone arrays like an Ambisonic microphone array. So this is a topic which I did in my master's degree. So it's basically to emulate space. As you can see, this is a nice octophonic room from Maynooth University, where the listener is at the center and 8 speakers are around. And I want to digitally simulate this room into a software, which is what you see here. These 8 knobs represent this 8 speaker, and the listener is from the center position. And there is also a paper published on this, which you can find from this link. And this is also open source, so you can check the Git and try and use it. So how we did this is basically we take dummy head microphone and we apply convolution as explained in the previous talk. But I'm not going to go in depth of this topic and explain all these formulas. I'm going to simply explain what I did. So I played sine sweep from each of the 8 speaker with respect to the listener's position. So we get for one speaker, you get left and right. So for similarly, I took for 8 speakers and I developed a application using a language called C sound, and then developed a GUI to build this software. So it does convolution in quasi real time, if not actual real time. But there are quite a few limitations here. Since the head mic is just fixed in one direction, what about if the heads are turning? So what will you do in this case? Or each and every humans have different ears, different body, different head sizes. So the sound coming from one direction and hit your ear is going to have some diffraction, and each humans are going to hear a different sound. So our ears are, it's called acoustic fingerprint for a reason, because every human have a unique hearing capability. So you have to apply an individual HRTF equalization before it reaches one's ear. So how do we do it? And finally, how do you get more spatial resolution? To address this, we use Ambisonics. Ambisonics is basically, it encodes a three-dimensional space using a set of mathematical functions called spherical harmonics. In the first order, it has 4 channels, where the W channel represents the sound pressure, and the other channel W, X, Y, Z represent 3 angles X, Y, Z. So in its first order, it has 4 channels. As the order increases, the channel also increases. The spatial resolution also increases. The file size and the processing restriction also increases. So we have to make a right trade-off and use the right microphone and use the right processing to get a real-time rendering of these signals in our headphones or in our speakers. We have already measured quite a few spaces and also quite a few cars using this microphone. As you can see here, it's a Zelia microphone. It has 19 capsules in it, strategically positioned so that it captures audio from all directions, and it can be encoded into the spherical harmonic domain for processing. So the advantages of this, you get high fidelity spatial reproduction for sound synthesis and NVH analysis, and also one big advantage of Ambisonics that it can be rendered into any mediums or any formats, 5.1, 7.1, Dolby, or even if you want to create your own speaker formats, you can also adapt to it by using sofa files. You can create a sofa file and use Ambisonic. So it's very flexible in terms of reproduction and rendering. And also with the use of a head tracker, or if you can track using your camera, your head movements, it can also dynamically adapt for better spatial sound perception. So the overall goal of my research here is to contribute to the advancement of autonomous vehicle technology using the role of sound and audio, and also inform the design and implementation that prioritize safety, efficiency, and passenger comfort so that the manufacturers can make the right decisions even before building, which saves cost, time, and also gives us better results. And to finally have a holistic understanding of human-machine interface in the context of autonomous driving. Thank you so much. And this entire research was funded by European Commission through Marie Curie Scholarship through the project Gap Noise. Thank you.
Any questions? Yeah.
Hi, Joshua. Thank you for the presentation. It was great. We at Harman also do something similar. But I have a specific question with respect to ambisonic reproduction, right? You said you can decode it to 5.1, 7.1, binaural, all of those. But in a car, it's a very specific case where you have speakers that have restricted frequency ranges. On one side, like one door you take, you have three different speakers: tweeter, mid-range, woofer. So the fundamental assumption in ambisonics is that there is direct line of sight. All sound decoded from one point in space. Come from one speaker, right? How does it sound when you decode an ambisonic recording into a car speaker system?
Very interesting question. Thank you. So I got the same question 6 months back, and I started investigating on it, and I came on a topic called crosstalk cancellation, where two speakers are placed close to your ear, which mimics binaural, but instead of using an headphones, you place two speakers in your headrest very close to your ears. That way, you can isolate your space. I think you're familiar with that concept. Using those technologies, you don't only utilize the line of sight speakers, but the ones that are closer to you. So the rendering is more personal.
Okay, thank you.
Any other question?
So I saw as many as 8 speakers in your setup. And there's this recent trend for MEMS speakers, right? So like, where is this thing going? Is it going to be like a lot of speakers all around because we already have so many cameras, of course?
The speakers in a car, you mean, right?
Yes, of course.
So it's going to be placed like the recent cars that are coming out. It's not just 4 speakers anymore or 8 speakers anymore. For example, recently a car in India came out with its first Dolby Atmos setup. And also the car I showed here, EV6, it has 16 speakers built into it. So the decision is made by the manufacturer themselves. This this theory proves a concept which builds a framework which anyone can take and apply it as they want. That's the goal of the research.
Nice. Thank you. Very interesting.
Right, we have one more question here.
Hey, Joshua. I have a follow-up question of this. So you mentioned something about crosstalk cancellation, right? So it's basically placing speakers right behind the ears of passengers. So are you planning to create profiles for different passengers? So like say someone is shorter and they're sitting in a car, their head position won't align with another passenger. So how do you address that issue?
Indeed, it's still an ongoing research. So how we are planning to approach is basically to have a speaker that will have a bit more wider depth of spread or depth of field, wider imaging. So it's still in progress that we have to find the how accurate it is translated.
So, any other questions?
So it's a very basic question. So I would like to know about what about the noise cancellation mechanisms that you use in the spatial audio there inside the vehicles? What kind of a progression that's happening there in noise cancellation techniques?
So noise cancellation and spatial audio are entirely two different approaches in acoustics. You don't necessarily need to control the entire noise or apply an active noise cancellation to render spatial audio. Noise cancellation can be approached in two ways. One is by using certain materials to block sound from entering into the car, which is an entire research topic on itself called metamaterials. They research on what materials to use and how they can insulate a sound. Another one is active noise cancellation, where you use yes, yes, it's basically how it
Okay.
works on headphones. It's
Yes.
very similar.
Oh, okay. Very similar. The same way that's
The
for the
concept,
3D spatial
yes,
also.
the theory is similar.
Similar.
Yes.
Oh, okay.
Any other questions? All right, I think we are good. So round of applause for Joshua for such an amazing talk. Thank you.